Hey, good afternoon, everyone.
Good afternoon, Professor.
Yeah,
Good
hi,
afternoon.
Mukhtar. Good afternoon, Sapphire. Let's see. I'm seeing three people here now, and in the forum, let's take a look at the today's forum. Okay. Yeah, three people only. Huh? What's going on? Um, it seems like everybody's getting lazy. Uh, okay, four, right? Um, all righty. So I see four people. Okay. So hopefully the rest of the class will catch on pretty soon. Okay. Let's see. So in our last class, so let me open my. Where's my? Oh yeah, whiteboard. Hey. Okay, whatever. Uh, what was my password? Just giving me a hard time. Try. Maybe not. Giving me a hard time again. Okay. All right. What's going on? Okay, let me just stop sharing a while then while I recover my password. It should be the one. It should be the one. Ah, okay. Seems like I'm. Okay, I. Oh, so I can't seem to recover my password. I'll have to first recover my password, and then I can use the. So this is crazy, huh? There. Alrighty. So since I'm not, uh, seems like I can't use the whiteboard for a while. So let me just. So let me share application again. All right. So I'll just have to use the. Okay, I'll have to use Excel. And hopefully now. So we were talking about the, oh, it doesn't allow me to draw. I cannot draw on this. This is a problem. Okay, let me try. Oh, okay, if I don't have that, I can also have either I can use also, what was that called? Yeah, OneNote. All right. Okay. So we were in our last class. We were talking about three types of commonly used logs, right? Logarithms. The first one is common log, right? The second one, binary. Binary. And the third one is natural log. And I told you, these two have some, they have limitations they can't take for long, right? So common log uses 10 as the base, right? So any number that is some powers of 10, right? Some powers of 10, we can turn it into right any log, right? If the exponent, if the base and the if these two numbers are the same, right? If these two numbers are the same, the base and that's base of the log, right? Basically, if they are the same, all the logs basically can allows moving the exponent to the front of the log function. So it's it becomes, it turns into a multiplicative function. What used to be a power function now becomes a multiplicative function. And that's the properties that we want to use, right? That's the properties we want to use. But as I said, it's not impossible. It's not impossible. It's just not very convenient when, using binary log or common log, because unless the number we are taking log of are powers of 10 or powers of 2, it's not easy to take log. It's not easy to visualize what this might be, right? So we're not using, we need something else other than, a common log or binary log. So the third thing we were talking about was natural log, and I told you natural log uses Euler's number. How do I undo this? Oh yeah, undo. So it uses Euler's number as the base, right? So in other words, you can take log of any number to base E. also written as natural log of x. But then, how do we? What is Euler's number? That's the most difficult question. And the Euler's number is basically, based on. So how do I move? Yeah. Oh. No. Hmm. How do I move? Okay. Yes. Yeah. All right. Suppose we all know basically uh, one if we have uh, APR um, and we basically raise it to T and we know APR can be adjusted by compounding frequency, right? Uh, what if, suppose, uh, APR divided by M, right? And then um, we know that because M is the compounding frequency per year, right? If we are compounding for T years, actually there will be T times M compoundings going on. If there are M, if the frequency of compounding is M per year, right? And what if APR is 1? 1 means what? You think one is, if you think one is 1%, then no. 1 is 100%, right? In percentage, right? 1 is 100%. So suppose, and if T is just 1 year, right? Then think about it. APR, just, assume that, at first APR, M is 1. Let's assume first M is 1. So annual compounding. So in that case, we'll just, rewrite it as 1, right? Because that's 100%. And we can ignore T because T is 1, right? Right. So it's going to be just, 1 plus 1 over M raised to M. Okay. Now, and if, because M is 1, right? This will be simply, the whole thing will simply be, the whole thing will be simply 2, right? But because, and what does that mean? That means, basically, if you put principal, right, And something like 10K, right? Something like 10K. If you put the principal in there and put it in the bank for 1 year, it's going to double, right? Future value will be exactly 20K, right? So this was the case when, APR is 100%, and M is just 1. But the reason APR can be anything. The reason I put 1 there is, it's easier to replace later, right? It's easy to replace 1 with anything later. But, basically, understanding that, let's stretch our, what if M is something else? Not 1, but, because we know M can be 1 or 2 or 4, 12, even 52. 52, 365, and whatnot. Let's try increasing our M. I mean, you've been thinking probably the maximum that M can go, M can go to is 365. No, actually, there's no limit. There's no limit. It can be, I said, theoretically compounding can happen every hour, every minute, every second, right? Even by nanosecond. But what is nanosecond? Nanosecond is, nano means 9. So it's, nanosecond means, 1/10 to the 9th. In other words, 1 billionth of a second. Or even, 1 to the 10 to the 12th, 1 divided by 10 to the 12th, whatever it may be. And in other words, if we split time into very small fragments, right? Now think about it. If as we are increasing M, what does that mean? We are increasing the compounding frequency per year, right? And if M goes, as M grows, this fraction will be a very small number, right? As M increases, isn't that right? As M increases, right, the whole thing will become the whole fraction will become a very small number. Again, so assuming that, keeping that assumption, right? If M, how far M can go? Well, it can even go to infinity, right? What's going on? It can even go to infinity. That means if we increase M to infinity, it's going to be a very, what's it going to be? What is this whole thing going to be? In other words, if M goes to infinity, what's going to happen? What's going to happen to one plus 1 over infinity, right? But again, because it will have to be raised to infinity as well, because basically we are raising it to t times m. T doesn't matter. We'll just assume t is 1 within 1 year, right? We assumed t is 1. So within 1 year, if we increase the compounding frequency to infinity, what's going to happen to this number, right? That was the question. And now think about it. What is this number going to be? Anyone? Anyone listening? What's that number going to be? Are you there? I see 11 people here. Not a single person can answer that. Are you guys there?
I'm here, Professor. I do not have the answer.
Okay, Tia and Claudia, thank you for responding at least. 2 people are responding. Two people have responded. So now think about it. What's this number going to be? When 1 over, when n goes to infinity.
Said 0?
Right? Who said 0? Who said 0? Who said that?
I said Mukhtar.
Mukhtar. Mukhtar, you're close, but it's not 0. It's not going to be 0.
Yeah.
Yeah. It's going to be, you might
What did it be, the number, infinity?
1 over infinity. Look,
So wouldn't
Is that 1? Is that 1?
No, you're dividing 1 by an infinitely large number. How can it be 1?
No, I'm asking the first number. That's a 1, right?
Yeah, the first number is 1.
Okay.
But my question is, I circled it with the highlighter. Right? If you're watching, you know what I'm pointing at. Because I circled that with a highlighter. Huh? Mukhtar said it's going to be 0.
I figured it would have been infinity number.
No. What does infinity mean? Infinity means infinitely large number. Right?
Yeah, any number, a long number.
No, Mukhtar, I said Mukhtar was close, but he wasn't quite right. Because think about it, logically, if you divide 1 or any number by an infinitely large number, what should it be? Huh?
Infinite.
No. That's not logical. Infinity, I told you, infinity means, infinitely large number. Right? When you divide 1 by an infinitely large number, how can it be infinity? Think about it. You're dividing 1 by even 100. What's it going to be? It's going to be 0.01. If you divide it by 1,000, it's going to be 0.001. If you divide it by 1 million, it's going to be 0.000, 6 zeros and 1. Right? And if you divide it by an infinitely large number, how can it become an infinity? It will be. Mukhtar wasn't entirely wrong, but Mukhtar was quite close, but he wasn't entirely right, because it will become something close to 0.
Does it just decrease? Is that what you're saying? It just gets smaller?
Of course, it will have to decrease. But what is the ultimate point of decrease?
Undefined? Because technically,
you're right. Undefined, but usually.
Do I get a point?
But undefined is too broad. It will be close to 0, right? It will be close to 0. So
1
at least,
over x?
no,
Maybe I'm not
what-
understanding the question.
I said Mukhtar's logic was correct, but he wasn't entirely correct. Okay, because he said 0, but it's going to be, look, you are also logically correct, because it's going to decrease, right? It will have to be a very small number, right? Because you're dividing 1 by an infinitely large number. It's going to become, it has to be an infinitely small number. So it's close to 0. It becomes a number that's close to 0. It's going to be like 0.0000, infinitely 0, and infinitely 0, and infinitely 0, infinitely 0, and 1. Something like that, right? So in other words, it's not exactly 0, but it is, close to 0. So so who said undefined? Who said decrease first? Who said decrease?
Claudia, I said both.
Okay, Claudia, yeah. So Claudia,
You know I need the points.
yeah, at least logically you got it right. So logically you got the okay, where's my pen? Jesus, when I need the pen, where is it? When I need a pen, so I'll give both you and Mukhtar 0.5, because it's the logic that matters. Where's the pen? Give me my pen. Give me back my pen. Where is it? Ah. Right. Okay, Claudia and Mukhtar, you're getting both 0.5. Okay. And today is section 14. But think about it logically. How else would you put it? I mean, it's going to become a very small number. Logically, it will have to be a very small number, right? So that's how you express it. Close to 0, right? It's also called asymptotically 0. Asymptotically, right? So now here's the thing: if this number is, if this thing is close to 0, not completely 0, then we're not done yet. Why? Because we have to answer what is 1 plus this number raised to the whole thing. We have to answer this, right? Now, suppose if 1 over infinity is 0, simply 0, this is an easy question to answer. If the whole thing, 1 plus if 1 over infinity is 0, then the whole thing will be just 1, right? The whole thing will be just 1. Why? Well, think about it. If this is 1 over infinity is 0, the whole thing is 1, and then raised to infinity. You raise it 1 to infinity, no matter what you do, it will just be 1. Isn't that right? But however, we're not dealing with 1. We are dealing with a number that is slightly greater than 1. We're dealing with the number that is slightly greater than 1. So in other words, we're dealing with 1.0000, right? Infinitely 0, and 1, right? But think about it. Then the question is, if you raise something like that to infinity, what's it going to be? If you raise, right, something that's slightly greater than 1, if you raise it to infinity, what's it going to be? Well, that is what Euler discovered, right? That's what Euler discovered. If you raise something just slightly greater than 1 to infinity, right? It's going to come to 2.718 something something, but it's going to go on forever. It's going to go on forever. And this is called Euler's number. It's called Euler's number. Now, and why is this important? Well, it's important, it's significant because whereas we had difficulty taking common log of numbers other than the powers of 10, or we had difficulty raising, taking binary log of numbers that are not powers of 2, right? As I said, mathematically it's not impossible. But it's not easily visualized. I mean, you cannot easily tell what it's going to be. So as I said, before, inevitably there is a limitation, right? There's a limitations to what number we can take common log of, or what numbers we can take of, a binary log of. But instead, we can take log of any number to base e. And why? Let's just say that it's because this is based on a number that is slightly greater than 1. I mean, think about it. You cannot take log of 1, because 1, think about it, there is no power, I mean, that can change 1, right? 1 to the 10th power. 1 squared is 1, isn't that right? 1 cubed is 1. Any powers of 1, still 1. 1 to the 10th is, 1 times 1 times 1 times 1 times 1 times 1 times. Anything you do, whatever you do, is still 1. So raising 1 to some power, it's meaningless, it's pointless. However, if it is, something slightly greater than 1, right? Something slightly greater than 1, infinitely, something slightly greater than 1, if you take, it would be the smallest number that can be raised to power, right? So let's do this. I mean, without further, I want you to, you have this file, right? You downloaded this file before, right? So we worked on that. So when you have it, so please open it in front of you. Open it in front of you and go to the bottom tab that says EAR or APY. And here, let's do this example. Do you have them? Do you have this file in front of you? You have this file in front of you, everyone?
I'm getting it now.
Okay,
Yes.
please have it. Okay, good. So I can't wait too long. But let's just do this exercise. So we have $1,000 principal, right? Suppose we have $1,000 principal. Make it 10,000, right? Because that's the example we've been doing. And then I'll make it. Okay, let's just make that 10,000. And 6% APR, 5 years. We know the answers to this. I mean, we've done these. So, but then let's take a look at the compounding frequency, column D. Column D, right? First is annual compounding, and let's see. So we are column I is only the multiplying factor, right? What they call compounding factor, because we're just gonna try out what is the compounding factor. First one, of course, we just do 1 plus APR, right? I mean, 1 instead of APR, just 1, 1, because that's what we were doing, right? And we divide it by compounding frequency and raise it to 1. And it's just going to be 2, as I said, because right? If m is 1, the whole thing, this thing will be 2, right? And then we're going to just drag it down. If it is semi-annual compounding, quarterly, monthly, weekly, daily, right? What do you see? The compounding factor or the multiplier increases, right? Of course, because the compounding frequency increases, it's going to increase. But it doesn't increase that much. I mean, in semi-annual compounding, the compounding factor will become, the multiplier will become 2.25, quarterly compounding 2.44, monthly 2.61, daily 2.71, 4, 5, 6. And what if compounding frequency is 1,000 times a year? 10,000, 100,000, 1 million, 10 million, 100 million, right? We increase the compounding factor. And what do you see? It doesn't, it looks like, we know the higher the compounding frequency, the greater the future value, right? And it looked as if it's going to grow to infinitely large number. It's going to grow to infinity if we increase it infinitely. But the reality is, no, it doesn't increase by leaps and bounds. It's, although we increase the frequency to like 100 million, billion, and even to infinity, it's not going to go up to a huge number. It's got a certain limit, right? And that limit is somewhere around 2.71828, 2.71828 something, right? So if you raise it to infinity, then what happens is this is, look, even if you increase it to infinity, it's just, somewhere around 2.7182818, right? So this is Euler's number. This is called Euler's number, right? And it's the basis of natural law, and it's the basis of, exponential function. So how do we then, of course, you don't need to calculate this. Excel is going to take care of everything, but having that in mind, now we can approach the question of natural law, right? So basically, natural law is, natural log of x. X can be any number. Is, log using e as the base, right? But that's not. And then that means we can take, remember, the reason we came to this is because of n, right? Remember, if n is the unknown, how do we solve for that? Of course, we start with, 1 plus r, okay, raised to n. And I told you this is like a cage, and this is like a padlock, right? You cannot open the cage, right? Unless you know unless you can open the padlock. But then this is currently now z equals x raised to y structure, right? Which is, power function. And I've been telling you, key to solving any equation, is to identify z equals x times y structure. However, we don't have that structure. Instead, we have z equals x to the y structure. So then how do we proceed any further? And I showed you that the by taking log, right? If we take log on both sides, right? And since we don't know, since there is no guarantee, there is no guarantee that these numbers are powers of 10, right? We cannot take, it's not that it's impossible, but it's not easy to take, common log. So then when these numbers are, just, a random variable, right? It's the best thing is to take the natural log. So then we take natural log of both sides, because whatever you do to one side of the equation, you must do the same thing to the other side of the equation, right? So if we take, and what is the properties of the log? When we take log, right, you remember the exponent can be moved down like like a coefficient, right? I explained this, with common log. If you have, log of 100 to base 10, that's log of 10 squared to base 10. And since log of 10 to base 10 is 1, right, it becomes 2, right? I explained that. So it becomes y, not n, right? So then this becomes what? Now this becomes z equals x times y structure, right? Now it becomes z equals x times structure. And solving for y, because y is our unknown, right? This is what we want to know. And we've turned it into a z equals x times y structure, right? So solving for y now, all you need to do is what? Anyone? Solving for y? Anyone? That's going to be simply natural log of. Someone's trying to say something, but too late. I'm already natural log of z over natural log of x. Okay? Applying the same logic to our equation. Now, this is our this is z, this is x, this is y, right? So what do? We have to take the log. So I take the natural log of the thing in the bracket. I'll just call it the thing in the bracket for now. And then natural log of 1 plus r raised to n. And again, thanks to the properties of log, right? This can turn into natural log of the left-hand side. Right-hand side will be n times natural log of 1 plus r, right? And then n is our unknown, right? This is our unknown, right? So we'll solve for n. Solving for n, we will have natural log of Fv over P over natural log of 1 plus r. Okay, so this is how you find n. This is how you solve for n. Now that took us that took a lot of our time. So we cannot we can we have just a couple of minutes left, but let's do this. Why is it all here? We did these examples before, right? So first, we know you will have like 24 something there. Let me raise to C18. That's one. Something not right. What happened? E18, A18 raised to C18. Oh, no, 1 over C18. What am I? 1 over C18. Over C18. You would have this, and then let's find what this is going to be. Okay, using it will be natural log of Fv over P divided by natural log of 1 plus B18, B19, right? There you go. It will give you 5 years exactly. Now again, for this one, it's just a matter of making an adjustment. But I would rather do it here because I know since we don't have much time, I'll just point to this. Times n. Or will be Fv over P raised to 1 over n is in F25 minus 1, and then APR will be minus. And here, if so you want to find n, first I'm gonna divide this by 4, so that will be quarterly rate, and then I'm gonna use natural log of Fv over P divided by natural log of 1 plus r. Enter. It's going to give me exactly 20. That's 20 quarters, but the question was in years, so then you will need to convert it into, right, simply divide that by M, that's going to be C26. What happened? Oh, D26, I'm sorry, D26. There you go. Okay, it gives us exactly 5 years. So that's all the time we have. Any questions so far? Everyone got the same?
I
Professor?
have a question about
Yeah.
this one.
Go ahead. Who was speaking? Who was saying something?
Oh, I wanted to ask about the homework because recently I was finally able to purchase it because
Mhm.
I just wasn't before because of financial reasons. But I was finally able to get it, but I wanted to ask, like, for the
Okay,
one
hold
that I
on.
didn't do, like, I didn't do the first
Hold on,
homework.
hold on, hold on, hold on. I will let me just dismiss the class first. So I have another class starting in like 5 minutes, so I can't stay long, but I will stick around. Um,
I have the
so
same question, Professor.
yeah, the
I'm on
class
the
is
same boat
dismissed.
as you.
The class is dismissed. If you don't have any further questions, you may be excused. So let me stop recording first.